Apart from general computer peripherals, the equipment required for this project were 2 Odroid U3s, 2 Wi-Fis, a Rover 5 chassis, robotic arm, keyboard, webcam, breadboard, pins, 3 L293D motor drivers, and lastly a 12-volt lithium polymer battery and a 5-volt step-down regulator. The Wi-Fis allow the Odroids to interface with each other, as the base Odroid will send user input signals to the bot Odroid and also receive the webcam byte stream. The bot Odroid in this case is wired to the webcam, robotic arm and chassis where inputs are received.
The electronics that came with the robot arm used 4D batteries for power, 2 supplying a negative voltage and 2 supplying a positive voltage. Using the circuit board that came with the arm allowed the controller to move each motor bidirectionally by either providing a positive or a negative voltage. This was an issue when it came to connecting the arm to the Odroid, as the batteries would no longer be used for the power supply, so instead 3 L293D motor drivers were used to drive the 5 arm motors bidirectionally, and the power was provided by the I/O shield. For each motor, 3 pins were connected into the I/O shield, input A, input B, and an enable input. This meant that the arm needed a total of 15 pins to be connected to control all of the motors. This used up most of the available pins on the I/O shield, which only had 16. This meant we didn't have enough pins to control the rover motors, which would be an issue we would have to fix later. Once we had connected all the motors to the I/O shield, we could test the functionality in the keyboard input in a Python program. The numpad keys were used to control the different motors, and this test demonstrated the core functionality that we would build the rest of the project from. The Rover 5 came with a L298P motor driver, which works almost the same as the L293D motor drivers for the robotic arm, but as this motor driver came on a board, we wouldn't need to wire up all of the pins, but instead just the input A, input B, and enable pins. We initially tested the functionality of the rover motors with an Arduino sketch, as we didn't have enough pins available on the I/O shield from the robotic arm. To fix this issue, we removed the enable pins for each motor and instead provided a constant input. This would still give us full control over the motors, as the enable pins functionality could be emulated by providing an input of a 1 or a 0 to both of the input pins at the same time. Doing this for all of the 7 motors saved enough space to fit all of the inputs onto the I/O shield. We needed to create 2 Python programs, one to act as a server, or the base, that the user would control the bot from, and one to act as a client, connecting to the base and sending the webcam data to be displayed for the user. The Python library Pygame would be used to handle the keyboard input and webcam output. The keyboard input was originally tested along with a custom library to control the output values sent to the I/O shield. This was then developed further by adding the webcam output. From here, the connection between the 2 Python programs was made to send the commands and webcam data from one program to another on a local host. This connection then had to be configured to work with the connection between the base and the bot Odroids that would use an ad hoc network to send the data. The keyboard inputs were sent from the base to the bot as unique strings that, when checked, would correspond to an output. This was written in a way that would allow for multiple inputs to be pressed at the same time and received so that multiple movements could be done at once. The base program allows for a connection to be made and dropped without restarting the program. This meant that testing could be done faster, and it also allows for the bot to be quickly reconnected if the connection is dropped. This program is also able to handle incorrect frame data without crashing. This is important because if the base program closes, then the bot will also close. This makes the base much more reliable. After configuring the programs to connect and send commands and webcam data to one another over the ad hoc network, an issue occurred with sending the webcam, as the received frames would begin incorrectly displaying on the receiving program. This issue was fixed by using buffers to store extra data that was received with each frame, as a side effect of the large amount of data that was being sent many times per second.
In order to create the network connection between the bot and the base,
research had to be conducted in creating the ad hoc network.
Ad hoc is a simple wireless network.
The Linux interfaces file had to be modified to include an ad hoc interface.
There was an issue that we wasn't able to solve. Whenever the system is rebooted, the interface doesn't configure properly upon startup.
As a result of this, the if up and if down WLAN2 commands have to be executed whenever the system is started.
After testing to ensure that the ARM and chassis functioned independently and correctly for input sent from the base Odroid, with as minimal input delay as possible received by the bot Odroid, the webcam, robotic arm, bot Odroid, breadboard and LiPo battery could be secured on top of a large enough wooden base tied to the chassis, concluding the building process. The webcam resolution needed to be made significantly smaller to reduce video latency. This was due to the raw RGB data stream being sent without any compression. The limited bandwidth available, the more compression required, and the higher the latency will be. It's specified that the claw can't carry more than 100 grams of weight, so expectedly it fails to lift twice that in the 200-gram water bottle. The robotic arm is able to easily lift small objects like controllers or pens without too much stress. This is a more realistic use of the robot's capabilities, as it would suit jobs that require more precision over strength. The completed project's mobility and dexterity make it effectively suited to job roles such as surveying an area from a distance and potentially moving small objects or retrieving small objects from without human interference. However, the prototype suffers from an issue of turning, as the Rover 5 motors do not have the strength, or the provided voltage is too low to allow the bot to easily rotate on the spot. The chassis is programmed to turn either left or right by moving each motor in opposite directions, although with the friction provided by the carpet surface, the chassis is not capable of turning with the current 9-volt battery powering it. This could be potentially fixed by increasing the voltage supplied to the Rover motors, or by switching the Rover 5 base with another with more powerful motors that can handle the weight of the completed build. The network connection is lost between the Wi-Fi dongles at approximately beyond 10 meters of unobstructed distance between the Odroids. This results in only the last input being received indefinitely at its point of disconnection, in this case the forward input.